on Thursday, we finished by looking at the heat equation, and we were talking about this problem here where you have a boundary condition at 0 and a boundary condition at pi, and it's an inhomogeneous problem. Okay, so this is 2 and this is 1. And for an inhomogeneous problem, you remember the trick is essentially to solve for the steady state solution. So you say I'm going to look for a solution u of x which is not dependent on time. This time derivative on the left goes away. You integrate it twice to solve ux x equal to 0, impose the boundary conditions, and this is the solution you come out with. Okay, so this is a graph that is set to be 2 at x equal to 0, is set to be 1 at x equal to pi, and that's essentially the distribution of heat that you would expect the system to converge to as time goes to infinity. Okay, and then what you do is you say, well, I'm going to write down the solution as a sum of this u of x, this capital U of x, plus a u hat that I'm going to determine, and you attempt to write down the equations for u hat. Okay, and when you write down the equations for u hat, you find out that it satisfies the same PDE. It satisfies 0 Dirichlet boundary conditions on both boundaries. But this is now u hat equal to 0 and u hat equal to 0. And the initial conditions change very slightly. The initial condition now has to be compensated by a capital U of x here. So you now need to solve for these Bn coefficients. So after you've done the separation of variables procedure, you now have this form, the solution. You now need to impose the initial condition and then solve for the Bn's. Okay? And the trick then is that, so you remember, so first of all, what does this look like? This is just this graph here. Let's just draw a picture. Okay, so when x is equal to 0, it's -2 here. And when x is equal to pi, it's basically 1 minus 2, so it's -1 here. It's the graph negated, like this. Okay, and you remember the idea is that if I were to give you a problem from 0 to pi and ask you to find the sine series, it's equivalent to seeking the odd extension of this function. So you want to go to -pi here and seek the odd extension. And the odd extension is just this graph here with all the values negated. So at the origin, instead of -2, it's at 2. And at this point here, instead of -1, it's at 1. Okay, so there's your odd extension. This, if you like, this is called FO of x. And then now you're ready to write down the Fourier series coefficients, these Bn's. So you'd write down Bn is equal to, and so it's a 1 over pi. Okay, I'll write 1 over pi like this, an integral from -pi to pi of FO of x times sine of nx dx, like so. And then, okay, this is an even function now because that's an odd times an odd. You can double up, so this becomes a 2, and you just have to integrate from 0. This is a 2, and you just have to integrate from 0, and you just integrate the function. And so here, the function is just this minus u of x, like this. Okay? So that's basically it. Let's just do this calculation. Okay, so now this is 2 over pi. Minus u of x is this function here, x over pi minus 2. So this is 2 over pi, an integral from 0 to pi of x over pi minus 2 times sine of nx dx. Okay, so now you want to do integration by parts with this. And if you remember doing one of the problem set questions for Fourier series, it's very similar to a problem set question for Fourier series. When you do integration by parts for this, my tip to you is to make sure you don't separate. You keep the x over pi minus 2 factor as together as your u, and then you let this be your dv. Okay, so here's your dv, and here's your u. Okay, so then this is 2 over pi, and then brackets you have u times v, so it's x over pi minus 2, like this, and then you have to integrate this function here, so that gets you a minus cosine n times x over n from 0 to pi. Okay, and then you're going to add 1 over n, the integral from 0 to pi. I'm going to erase this u here, getting in the way. And then I have to differentiate the u function here, so I have a 1 over pi. And then I have to put in this minus cosine of nx. So the negative I've already used here for the integration by parts. So this is just a cos of nx dx, like so. Okay. So now, if you want to, you can integrate it again. So you can integrate this step again. But the trick is that you'll notice that if you integrate this function, you have a the cosine of nx becomes a sine of nx function, the 1 over n factor. And then you substitute in 0, you get sine of 0, which is 0, and you also substitute in pi, and you get sine of n times pi, which is 0. So this thing here will then be equal to 0. Okay? If you didn't know that, you would have done it and you would have figured it out. Right? It just takes one extra step. Okay, so then at this point, you just have to substitute in the two limits. You have a minus 1 to the n from the cosine of pi x, and then a minus 1. So it looks like you have 2 over pi. Oh, sorry. So if I put in pi here, I get 1 minus 2, which is a minus 1. So I have a minus 1. I have an over n factor. And then this becomes, too many negatives here. So this becomes a minus negative 1 to the n. I'm going to save myself and just move the negative out here. Change it to a plus positive, just so we don't screw up the signs. That becomes a negative now. And so I have a minus 1 times minus 1 to the n. And let's move the n out as well, just so there are too many negative signs floating around and might screw things up. So this is a pi, and then smooth the n out like this. Move that n out. We've moved this negative here, and so this is going to be a minus 1 times a minus 1 to the n. So minus 1 from this factor, minus 1 to the n from this factor here. And then on the other side, you're going to put a 0 into the x here. This becomes a minus 2. This is a negative, oh geez. It's minus negative 2 times the cosine of 0, which is 1. So I think this is that. Hopefully I didn't make a mistake there. Woof. Yeah, okay. Fine. Well, we'll figure it out in a second whether I've made a mistake or not. But so then we can feel free. So that becomes a plus 2. So it's a 2 minus negative 1 to the n with a negative in front. Okay, so let's erase this, and then we'll make a final conclusion, and then I'll show you a plot of this, and we'll make sure whether the answer is right or wrong. I can feel free to erase this thing here. I'll erase this thing here as well, and go down to that last line. Okay, so there's my Bn. Let's move. Should we move this negative out? Yeah, let's move this negative out there, so that becomes a 2 over pi times n. And then in brackets, it's going to be a minus 1 to the n. And then we move one of the negatives out, and so that's a minus 2, it looks like. Okay. Hopefully, I've not made a mistake. All right, so let's see. So that's basically it. That's the end of the story. We've completed the problem. Let's see whether the graph makes sense from the numerics. Okay, so I'm going to share my screen here. First, make sure I don't have anything embarrassing. Okay, so let's walk you through the same codes. And just remember, I've started posting these codes on the website, so you can download them for yourselves and run them yourselves if you want to, but they're not too complicated. Okay, so the code starts off by just clearing all the variables and closing all the figure windows. It sets 20 modes. Actually, this problem 20 ends up being well sufficient for it. You'll see that 20 it still looks pretty good. And then I've created this R function here, which is going to plot that expression that we had before. So 2 over n pi, yeah, times minus 1 to the n minus 2. Okay, that looks good. Looks like what we derive. Times the sinusoidal sine of nx times an exponential of minus n squared times t. Okay, usually this is n squared times kappa times t, but remember for this problem, kappa is equal to 1. Okay, and then the domain is from 0 to pi. That's what this next line, two lines do. It just sets x to be a vector from 0 to pi with 1,000 elements in there. And then we create a mesh of points in time. So we're going to solve from time 0 to time 5, and just with 200 points in between there. These next couple lines will plot the steady state solution. I'll show you in a second, but keep an eye on the blue function. And then it's going to construct so for this outer loop here is going to run through all the time elements. So it sets tj to be the jth time. It starts the solution off. So you have to remember that you want to plot u, which is a u hat plus a capital U of x. So this is the capital U of x. Okay, this is the steady state solution. And then it just runs through each element of the series and adds on each element. So u plus r with a different value of n for each of the different n's from 1 to capital N. And then it plots everything. Okay, so here we go. So let's run the code. All right, so this is what it looks like. Okay, so this is that time t is equal to 0, and the blue curve is the steady state solution, right? So what we're expecting is that as time increases, eventually the heat distribution in the bar will approach this blue curve. This is the curve that we derived previously. It's just the line that connects temperature 2 with temperature 1. Remember that the boundary conditions for this problem is that the temperature on the left-hand side is 2 and the temperature on the right-hand side is 1. And the initial condition is such that it starts off at 0. Okay, so this is a solution that looks, approximately like 0 at time t is equal to 0. And then now we're going to start the simulations, and you're going to see basically the heat distribution. So you think of this as like a cold bar, right? The bar is at 0 degrees, and the ends are one end is being heated to 2, one end is being heated to 1. So eventually the bar will warm up, right? Starting from the ends, and then the core of the bar, somewhere in the middle here, will eventually warm up. So here we are. And indeed, it approaches the steady state solution. Okay, and it approaches steady state solution, and it'll eventually get there in infinite time. Okay, now I just want to confirm for you that it does look right if I set the number of modes to be higher. So instead of 20 modes, 20 terms of your Fourier series, or 21 terms if you count the first term, let's use a slightly higher number. So let's use, say, 100. Let's quit this here. So now let's say use 100, and what we should see is that very first approximation, which looked, it didn't look so good. It was supposed to be 0 within the bulk of the bar. It's now looking, well, actually it doesn't look so much better. Even at 100 modes, it doesn't look so great. Okay, so you see now it's closer to the initial condition of 0, but you see because of the Gibbs phenomenon, so these oscillations which occur at the points of discontinuity, it's still not great. Right? So you'd have to go to much higher to reduce the oscillations within the bulk. But as soon as time is greater than 0, you see it actually looks really good. Okay. one of the effects of the heat equation is essentially to smooth out any discontinuities in the system. And that's something that I might mention in a future talk. But you might say that's one of the characteristic behaviors of heat. Heat has the effect of taking sharp points and then diffusing it, kind of spreading everything out. And that's why you see the oscillations right away. As soon as you start time, the oscillations go away, and then it becomes a nice smooth curve. Okay, good. Let's return back to the board. Oh, actually, before I return back to the board, no, that's a good idea. I want to just summarize everything. So that's the end of the story. You now know how to solve the inhomogeneous heat equation with inhomogeneous Dirichlet conditions. Okay, and remember the trick is first solve for the steady state, remove this time derivative, solve for the big U function, apply the two boundary conditions for the big U function, shift the solution so that it shifts it by the big U plus an unknown U hat, solve for the U hat, which is now a standard homogeneous Dirichlet problem, and then solve for the Bn coefficients just with the usual integral, and then you're done. Okay. So now what we're going to do is we're going to do a problem set question. I'm going to look at one of the first problem set question, where instead of these Dirichlet conditions, it's going to replace it with a Neumann condition, but it's going to be the same procedure. So I'll flash back to the screen, and we can read the problem set question together. Yes, that's right. So there was a question, which is, if you change kappa, would that make it tend to the steady state faster or slower? So changing kappa is a number that appears here, and it's the number that characterizes the heat properties of the solid, right? So different solids will have different heat properties. Some solids will spread heat faster than others, and you can see what the effect of that is. Essentially, with a non-unity kappa, if kappa here wasn't equal to 1, it would essentially insert a kappa into the exponential function here. And because the exponential function controls sort of the decay or the main shape of the curve, right? It sort of controls how quickly you approach a steady state or how quickly you approach 0. Then changing the kappa here will change that approach. So some will approach steady state very fast, some will approach steady state not so fast. Okay, so yeah, so let's flash our screen here. So then this is the problem set question I want to look at. So just to fill you in, there's basically problem set 8, which is now our return to the heat equation. Then there's problem set 9, which is our return to the wave equation. And both problem set 8 and problem set 9 are very similar in techniques, right? The only difference is one is for the heat equation and one is for the wave equation, but they're still the same kind of Fourier series techniques. Okay, so this question here is asking you, take the same heat equations before. It looks like I set kappa equal to 1 here. And the only difference now is that instead of 0 Dirichlet conditions, so remember Dirichlet is for this function value, I want you to solve the 0 Neumann condition problem. So you're going to set the derivative of the function equal to 0. Okay. Physically, what does this correspond to? I think you encountered this question on a previous problem set, right? So one of the problem set questions, 2 or 3 problem sets ago, had asked you, what is the physical significance of these conditions? And the idea is that because the heat flux is minus k times grad U, so the heat flux is proportional to the derivative of the temperature. This is equivalent to basically capping your bar. So you've taken a bar of length L and you essentially cap it with an insulating material that doesn't allow heat to flow out or in from that. Okay, so whatever your it's like thinking, you know, you've capped it with rubber, for instance. Okay, so this is a problem where you start off with an initial temperature and your bar doesn't allow the heat to escape from the ends. There's no heat flow from the ends. The other way of thinking of it is like you're starting with a heat distribution in a cooler. You know what a cooler is. You know, put cold or hot items into the cooler. And that cooler is designed so that the boundaries are thermally insulated, and that's what this condition corresponds to. Okay, so the question is essentially asking you, let's do the separation of variables procedure for this problem, and then let's get the Fourier coefficients. And what I'd like to do is so this is it. When you sit down and do it, you'll see it's exactly the same techniques as before. But what I'd like to do is I'd like to give you an actual f of x, and I'd like to plot the solution, and you can see what it looks like. Okay, so let's go back to the board now. Right. So I'm going to replace this, our picture here, which we've used now over 2 lectures. Let's just replace that with that problem set 8 question. So in that problem set 8, actually, you know what? Let's do it with the kappa in here. We might as well. It doesn't require much effort. We'll keep the kappa in there. You have the heat equation. So let's do problem set 8, question 1. You've got the heat equation, and the only difference is that this is now a ux, and the problem has asked you to do it for a general domain. So rather than the domain of size pi, we'll do it for the domain of size L. So this is 0, and then ux at L and t is equal to 0. And we're going to do it for now with a general f of x function. So this is the initial condition. So this is a bar, which you can think of these ends here as being thermally insulated. Okay, so it's capped with some material that doesn't allow the heat to flow. And as I said before, you know that because the flux is equal to minus k times grad t. Or in one dimension, it's minus k times dt dx. So setting this equal to 0 essentially is equivalent to setting the flux equal to 0. There's no heat flow. That's the physical interpretation of these 2 boundary conditions. Okay, so the step is going to be the same as the algorithm that we set out before. You first make sure that the problem is homogeneous. If it's not homogeneous, you again have to solve for the steady state solution. It is homogeneous here, so step 0 is satisfied in that algorithm. I don't actually remember the steps of the algorithm. And then the next thing you do is you separate, and then you solve for those separation constants, and you form the superposition of solutions. Okay, so let's start there. So you know, you're going to check that it's homogeneous. Okay, and then you're going to separate your solutions. So you're going to write your u as a capital X of x times a function of t. I usually like to use a big T just because I think of it, you know, time. But if you're sometimes you use temperature for T, so I think that's why the problem sets the notes sometimes use a G function instead. Okay, then you substitute this into this, and you separate, and so you have a time derivative on the left. We'll go ahead and do the separation. We'll move the kappa to the left-hand side, and then we have 2 x derivatives, and then we've divided the x over from the left-hand side. And then this is equal to a constant. Let's set that to a sigma, okay? And you can verify all the different cases as well. So verify the different cases. Now, I'm not going to verify the case where sigma is greater than 0. In that case, you have exponential growth in time of the solutions, and you have a trivial solution. We'll do the case where sigma is equal to 0, and then we'll do the case where sigma is less than 0. Okay, so case 1, which is sigma is greater than 0, you have trivial solutions. And you should go ahead and check that yourselves. But it's the same reasoning as for the Dirichlet problem. Right, so now we have case 2, and let's just do the sigma equal to 0 solution. So the sigma equal to 0 solution, you have t prime is equal to 0. 2 equations to solve. T prime equal to 0. And you have x double prime equal to 0. So t is going to be a constant, and an x will be a linear function. So here t is equal to a constant c, and here x will be, say, ax plus b. Okay, and then you have to impose the boundary conditions. So you have to go and figure out what the boundary conditions mean for big X. So ux at 0 and t equal to 0 tells you essentially that x prime, so let's write this as equal to x prime of 0 times t of t, and this is equal to 0. So the two boundary conditions will be equivalent to setting the derivative of x, big X, equal to 0 on both ends. Okay, so I'm going to go ahead and write that down. And in fact, let's write that down. Let's write it down over here. So the boundary condition will be equivalent to x prime of 0 being 0 and x prime of L being 0. Okay, so now you impose this condition to this function, and the only linear function that has the derivatives being 0 on both ends is just a constant 1. So this would tell you that x of x is equal to a constant b. Okay, and you're left with the conclusion that the solution of the sigma equal to 0 case is that both x and t are constant, and so u is constant. So together, these would imply that u is equal to a constant. Okay, that will be essentially be the a0 over 2 term of your Fourier series. Okay, good. So now you're ready to do case 3, and case 3 is the more typical case of this being less than 0. You could have combined case 3 and made this to be equal to a minus lambda squared. And then you could make this to be less than or equal to 0, and then you would have done case 2 and 3 together, but now we'll do that case. So this is now case 3. And so sigma here is minus lambda squared, which is less than 0. And then you solve those two equations, and it's the same as the Dirichlet solution that you had before. Everything's the same until you impose the boundary conditions. So you would have concluded that t of t is a constant times an exponential of minus lambda squared kappa times t, and x of x is a cosine and a sine. Okay, so you have a times cosine of lambda times x, plus b times a sine of lambda times x. Okay. So now we're ready to impose those two boundary conditions. Okay. And so previously, when we had the Dirichlet boundary conditions, this was just x of 0 being 0 and x of L being 0, and it essentially destroyed the cosine, and we were left with sines, if you remember. Okay, so how does this problem change if it's a derivative condition? Well, I first need to differentiate this function, so let's go ahead and differentiate it. So x prime is equal to minus lambda a times cosine of lambda times x, and then this will be a plus b times lambda times sine of lambda times x. And then you'll substitute in x equal to 0 into this, and then x equal to L into this. Okay, so firstly, x prime of 0 being 0 tells you that if I set x equal to 0, the sine will go away, and I'm left with a cosine. And so a times 1 is equal to 0, or a is equal to 0. On the other hand, I then set x prime of L equal to 0, and I'm left with the conclusion that b times lambda times sine of lambda times L is equal to 0. So this tells me that b times lambda times sine of lambda times L is equal to 0. What would I do without the chat, right? Okay, so this becomes a sine, and this becomes a cosine. I'm silly. Okay, then I set x equal to 0. Someone in the chat said, oh, you've not differentiated your trig functions right. Okay, so then x equal to 0, the a disappears. The conclusion is that b is equal to 0. And then x prime of L here, the b has disappeared. I'm left with lambda times a minus lambda a times sine of lambda L is equal to 0. So I think we're okay now. Would I expect you to check all the cases? No, I don't expect you to. It depends on the context of the question, okay? And who knows what's going to happen to the exams. If you look at the previous exams, most of the lectures never ask you to check the cases. We expect you to have a good understanding that the only non-trivial case is the lambda less than or equal to 0 case. In general, I do expect you to check the lambda equal to 0 case, so the sigma equal to 0 case. So that was case 2 in our case numbering. But I don't expect you to check case 1. You could, if you wanted to, simply say, in case 1, if this constant is positive, you have a trivial solution. Okay? Yeah, that's unless you're explicitly asked to check the solutions. So if you look at the problem set questions, one of the problem set questions does ask you, can you check explicitly the different cases and show whether or not you have a trivial or a non-trivial solution? Okay, so at this point, I have lambda L is equal to 0, and sine of stuff is equal to 0 if that stuff is a multiple of pi. So at this point, you're ready to conclude that lambda L, unless you want your big A to be equal to 0, which you don't because then you have a trivial solution, this should be a multiple of pi, n times pi, where n is an integer, and therefore lambda is equal to n pi over L. Okay, I'll rewrite this up here just because I realize it's being crammed in the video. Okay, so remember that this is, at this point, I'm happy for you to index this with a lambda n, right? So that it's just a notation thing. So rather than saying, I've got different constants, lambda is equal to n pi over L, you simply say, well, I'm going to index each constant with a sub-index of n here. Okay, and then the other thing to keep in mind is whether or not you need all the different n's. Do you only need the positive ones? Do you only need the negative ones? And do you need the 0 one? So let's just, we'll make a final conclusion and then we'll write that out. So we concluded that you have two possibilities, right? So either u is equal to a constant. So either the case where sigma is equal to 0, u is equal to a constant. That was one possible separable solution. For the Dirichlet problem, that constant turns out to be 0. Okay. For the Neutron problem, you can actually have a non-zero constant here. And in the case where sigma is equal to minus lambda squared less than 0, you concluded that u is essentially, we'll write it in full, so it's essentially a constant, let's call them ANs, times a cosine of n pi x over L times an exponential. Okay, let's write the big exponential form here. So this is a n pi x over L squared kappa times t. Okay, if you don't remember why these, so this is your lambda. This is your lambda n. And so this is lambda n squared, and then this is lambda n times x. And you've just simply substituted in the value for lambda. It's a very good question to what happens if you don't move the kappa over. The answer is that nothing happens. You end up with the same answer. And I'll quickly mention that in a second. Okay, so let's get to the very end here. So if n is, so what happens if n is positive? What happens if n is negative? What happens if n is equal to 0? So if n is negative, right, then the cosine just destroys that. So essentially cosine of a negative number is a positive number. So you only have to keep in account the positive n's, basically. So n is equal to stuff. If n is equal to 0, then lambda is equal to 0, and you're left with this case here. But you also get it for free at this point. So n is equal to 1, 2, 3, 4, and so forth. Okay, let me just repeat that. If n is negative, right, then the cosine of a negative number is just a positive number, so it doesn't matter in the end. So you don't have to include the negative n's. It doesn't change the totality of separable solutions that you have. If n is equal to 0, because lambda n is equal to n pi over L, if n is equal to 0, then lambda is equal to 0. So you're not actually in the case where sigma is strictly less than 0. You're in this case, but you would have gotten it for free because you would have concluded that cosine of 0 is 1, and you just have a constant. So in a sense, this case is included in that case if I let that to be less than or equal to 0. Okay, so you would have then you add everything together. So this is the superposition step, and I would like to rather erase this here, and then I'll write the superposition step here. So I'm going to write it right there. I'm going to erase that. So now I superimpose everything together. I go from 1 to infinity. And I'm going to treat the 0th one separately. So I'm going to have an a0 over 2 here, plus that. Okay. Let me say a word about that step. So this is the constant solution, yeah? And in the case of the constant solution, this exponential is just 0. Sorry, it's e to the 0, so that's just 1. So this is e to the 0 if you like. And then you just have the regular series from 1 to infinity. Notice here that I've introduced a factor of a half here, so I've redefined the a0 so that it has a factor of a half. That just makes the computation of the Fourier coefficients work out. Now suppose that you forgot to do that, and you said, I'm just going to let this be a0. Okay, that's also fine, but your a0 Fourier coefficient will then be off by a factor of 2. So you're better off being smart at this stage and just introducing that factor of a half. And there I am. Okay. Okay, so that's basically it. It's the end of the question. So you see it's very, very similar to the sine series that we had before. The only difference is your cosine Fourier series. Okay, so the Neumann problem, the case where you have a derivative here being 0 and a derivative there being 0, is the same as the Dirichlet problem. The only difference, instead of a bn sine of this combination, it's now an an times cosine that combination. Okay. I want to say a quick word about this question of what would have happened if we didn't move the kappa over to the other side. And I'll do that here. The answer is that it's not going to change the final answer that you have. So the question, I think, was, suppose that when I did my separation, I had a kappa xx over x here. And I didn't move that kappa to the left-hand side, I kept it on the right-hand side. Okay? Well, then you're going to let that be minus lambda squared, which is less than, let's just do the less than or equal to 0 case together. And then you go ahead and solve those ODEs. And when you solve those ODEs, your time equation is then a constant times an exponential, and instead of a lambda squared kappa t, this is now just a minus lambda squared times t. So there's no kappa here, but you get it in the x factor. So then this is going to be a times cosine here of lambda over root kappa times, yeah, I think times x plus a b times sine of lambda over root kappa times x. Okay, so the kappa no longer appears in the time term. It now appears in the sinusoidal terms. But then when you go and take the derivative of this and impose the boundary conditions, right, you end up with the same reasoning as before. The b will be equal to 0, right? This kappa is not going to change that. And you're left with making an argument on the value of this at x equal to L. And the argument will essentially be that you need sine of lambda over root kappa times L to be equal to 0. Before we only had lambda times L, right? And so now you have the root kappa sticking around, and so your lambda instead will be n pi over L with a root kappa on top. Okay? But then you see, well, I'm going to substitute this into here, and it all cancels out. I'm left with n pi x over L, the factor. So if you didn't move the kappa over to the left-hand side, it would just hang around at this stage. But when you go and find your lambda n's, the kappa then appears, and so you're left with the usual factor of n pi x over L is here. And you'll notice that in the exponential, the kappa then appears as a root kappa squared, and you're left with the kappa on top here. And so you end up deriving the same solution as before. It's not as kind of elegant. I prefer to move it over to the left-hand side because then I don't have to deal with these root kappa factors during this intermediary stage. Okay? Okay, so that's the end of that part of the question. The next part asks you to derive an expression for the ANs, okay? And so for that, you have to impose the initial condition and then derive your Fourier series coefficients, okay? So I'm going to impose now the initial condition. So therefore, the initial condition tells me that f of x must be equal to the value of this expression here at t is equal to 0. So you just set t is equal to 0 here, and you're left with the Fourier series. In fact, this is now an an times cosine of n pi x over L. Okay? So this looks a lot, it is exactly the Fourier cosine series. And so how do you find the an coefficients? Well, you have to do the same trick as with the even extension. So let's talk about that trick. I really didn't want to erase this, but it's too late now. Remember here that the f of x is a function that I've given you, right? So you're told what the f of x is, the initial condition of your problem. So let's say the f of x looks like this. So this is pi. This is L. This is 0, and this is your f of x. Okay, and so again, it's the same trick as for the Dirichlet problem. You would have said, well, suppose that, let me forget about this whole heat equation problem. Suppose I asked you to tell me what the Fourier series is for the 2L even extension of this function. So you say, I'm going to first form the even extension, so I'm going to mirror it about the axis like this. This is now fe of x for the even extension. And you would have concluded that the even extension is exactly this. It's the cosine series. And the an is then just, 1 over L, the integral from minus pi to pi of fe, and then you double up again. So that becomes a 2 over L, the integral from 0 to L of f of x times cosine of n pi x over L dx. Okay, so it's the same trick as for the Dirichlet problem. You considered instead the even extension over this should rather read minus L to L. Thank you. you form the even extension, and then you say, oh, hey, look, if you ask me to get the Fourier series for the even extension, these are just the coefficients, okay? And that's it. That's all you have to do. You just have to integrate that function, and then you're done. I want to show you what it looks like. And apologies because I'm going to take another 5 minutes of your time. I want to just do an example of what it looks like, and it's really nice to see the numerics of that, okay? So I want to make up an example for you where this is equal to sorry, we've gotten to the point where I can't remember what the example I actually used. Okay, yes, I remember now. So I'm going to make up an example for you where I'm going to set this to be x squared. Okay, so I'm going to say that the bar is heated initially to look like an x squared function, so it's cold on the left-hand side and hot on the other side, and set this to be equal to pi, like this. And we're going to set the kappa equal to 1, just for simplicity, and set this L to be equal to pi. Okay, so I'm giving you an actual problem to solve now. This is the heat distribution at initial time at t is equal to 0, Neumann conditions on either end. So think of it like it's a bar which is hotter on one side initially, but then it's thermally insulated, so heat is not allowed to escape. And you'd like to find out, oh, what does it look like? Or you can think of it as, I suppose, you have a very long cooler, and then you put something into the cooler which is hot on one side and cold on the other. And you're asking, heat is not allowed to escape from the cooler, what eventually happens? Okay? So this will be the same formula, right? And you just have to integrate the x squared function now from 0 to pi, right? So the solution is then u of xt is equal to a0 over 2 plus the sum from 1 to infinity of an times cosine. This is an n pi x over L, but L is equal to pi, so it's just n times x. And then you have the exponentials. This is an e to the minus n squared kappa times t, but kappa is equal to 1, so just minus n squared times t. And then I can verify, so I have to do the calculations. So this is a 2 over pi, an integral from 0 to pi of x squared dx. Okay, and you can verify that this is basically 2/3 pi squared. And then I have to do the other calculation for the ANs. This is like 2 over pi, and then you integrate x squared times cosine of nx dx, like this. So you have to do integration by parts twice. And this gives you 4 over n squared times minus 1 at the end. Okay? Then I want to have for breakfast yet. Right, so let's plot this. Let's plot this, and then we can go have breakfast. Okay, so I'll share my screen again. So this is going to plot that function that I just wrote down on the board. Okay, it's going to, so you remember the a0 over 2 coefficient is this thing here. So it's 1/2 times the a0 function I wrote, the a0 value I wrote down before. And then I have to add to each subsequent term of the Fourier series. I'm going to add each subsequent term, and that's this expression here. It was essentially 4 over n squared, 4 over n squared times minus 1 to the n, times cosine of nx, times the exponential of minus n squared times t. Okay, so let's plot that. And you see, actually, basically, because it's a smooth function, because you're trying to solve for the even extension of the x squared function, which ends up being smooth at the origin and smooth at the ends, the Fourier series, even with just 20 terms, it looks really good, right? So you notice that at t is equal to 0, it's bang on. The blue is the initial condition. The red is your Fourier series approximation, okay? And let's now run that. And what you should see, well, I'll play it and you can notice for yourself. But remember that in this problem, the boundary conditions are set that the derivative ends up being 0 at both ends. So immediately you should see essentially that the derivative is 0 on the left-hand side, which it's already, but the derivative on the right-hand side will then be 0. Okay, so here we go. And remember, it's hot at the right-hand side, cold at the left-hand side. Okay, so as I indicated, it's like putting something hot into a cooler. You know, one side of the cooler being set to initially cold, the other side of the cooler being set to be hot, but heat is not allowed to escape from the cooler by the boundary condition. Eventually, what happens is that the heat diffuses everywhere within that cooler, and it just becomes the same temperature everywhere. Okay, and it's an interesting question for you to ask: what is the temperature within the cooler? So what is this constant temperature that eventually the system approaches? And that's I'd like to leave you with that question, but I'll make an observation. The observation is that the area under the blue curve, the initial curve, is pi squared, right? Because it's well, it's not quite the area, but you'll notice that when x is equal to pi, this right-hand side is at pi squared because it's x squared, yeah? And you'll also notice that this height here looks suspiciously like pi, okay? So you can, I'd like you to go away and think about it, or not. Go away and think about it, but try to ask yourself, how could I have predicted what the height of the eventual curve is? And there's an energy conservation principle in there, right? In essence, heat is not allowed to escape from the cooler because the ends are insulated. And so whatever total heat you begin with, which is proportional to the area of this curve, it should somehow be related to the constant that you observe for this red line. Okay? So otherwise, that should get you started on problem set 8. Hopefully, we all find out soon what's going to happen with the assessments. But otherwise, I think it was a good lecture. We covered 2 interesting problems, and then next week we're going to go on to do the wave equation. Otherwise, have a good, just see whether I need to say anything else. I don't think I need to say anything else. That's basically it. So this puts an end to this chapter, chapter 15, on Fourier series on the heat equation. Next week, we're going to turn to Fourier series for the wave equation. And I think the week after is actually Easter. It doesn't sound like Easter, but it will. I think it is Easter. And after that, there's one extra topic, but depending on the way the assessments work, we'll figure out what happens. Have a good weekend otherwise. Enjoy the nice weather if you can. And I'll see you next week.